Hello everybody, welcome to today's session. We are still in the era of pre-training and fine-tuning. It is just the step before the large language model and the step after the transformer was invented. So it is in between. Last time we had learned GPT, and now we are going to learn another improved pre-training and fine-tuning model, which is BERT. BERT got introduced in 2019. The scientists who invented this BERT are these four scientists, Devlin, Chang, Lee, and Kristina, and let's take a quick look at their profile. Here is Devlin, we have Chang here, Lee, and Kristina. Today GPT is the most powerful, but you see there was a time when BERT, which was coming out from Google, overtook OpenAI in terms of all the SOTA score. In all the three cases, you see BERT has outperformed GPT. So what is the argument why it could do this? Let's learn that. They said that basically the NLP task can be broadly classified as sentence level task. For example, natural language inference or paraphrasing, where you need deep understanding of the sentence. And another is the named entity recognition or QA, where you need token level understanding. While Elmo focused on pre-training, and then during the fine-tuning, they had to make a lot of changes in the architecture for the task-specific architecture. But GPT reduced it, if you remember in our last video, through the traversal type approach, actually was able to reduce the need for the model architecture changes. Nevertheless, both of them used the causal masking, which means that it had access only to the left side of the token and the right side was masked, right? So, in order to understand this difference between unidirectional and the bidirectional, if we just go back to our self-attention video, multi-head attention of the encoder had only the padding task applied there, whereas the multi-head attention for the decoder had a padding mask as well as the look ahead mask, the causal masks. Both of them were applied. As a result, when we built our GPT, found that the tokens were feed it into the model used along with the causal mask, which means that when the first token is arriving, we are expecting the second token to come out as a prediction of the model, not as an input. When the x1 is given, we were expecting x2 to come from the model output, not as an input. When x2 was given, x3 and others were hidden. That is what is the basic architecture, right? This was also presented in the mask form, that when first token is appearing, the look ahead mask or the causal mask actually prevent all the right side of the tokens to appear in the input of the model. And this is what we presented here. But that was also combined with the padding mask, and together they form the final resultant mask applied on that. Now, what is the implication of this? The implication was that if there is a sentence called I made a bank deposit, bank had access to the left side of it, left side of the tokens, but not the right hand side. That is what is shown here. So therefore, this is a weak context which the bank is getting. It's not understanding both right and left hand side. As opposed to that, if we had to use the encoder architecture alone, okay, it's a transformer encoder only architecture, then we actually during that time, because the mask which is applied is only padding mask, which is where you have the zero. Padding mask is those which are the at the very extreme end, we have the zeros added, pad added to make all the sentences equal. That's what is there. But nevertheless, if we consider there is one token which is T5, it has got access to both the left side of it and the right side of it. Which means, if we take this example of I made a bank deposit in summer when I reached California, then in that case the bank has access to I made a as well as the deposit. So it has got both the left and right hand context. So that is the benefit to what we saw when we saw the score of BERT versus GPT, and that's what is the argument of BERT actually. Okay. Now let's go and see what is the problem if we have to do this. The problem here that then what the model will predict. I have already given what is the next token as the input. So model has no job to predict that. Therefore, the language modeling task actually fails if we have given access to both, right? Therefore, we substitute this task objective as masked language model, not the language model, but the masked language model, which essentially means that we are randomly dropping some of the token and replacing them as a mask. Example is here. For this particular sentence, we are randomly masking I, masking A, and masking here is the summer. These are what is masked, and that's what the model need to predict, this masked token. That's how, they applied this trick. The second task was also there. This was the multitask objective. The second task was basically predict the next sentence, which is you divide the sentence into two. First sentence is up to this in, and second sentence is when I reached California. And then you separate them by a separator. The task is here that if given the first sentence and the second sentence, which could be the logical one, or it could be a different randomly predicted one, wrong, then you are asking, classify them, whether it is next sentence or not, true or false, right? So it is a transform architecture we already learned. They used 12 to 24 layers, and then they used a large corpus, and just note this, 1 million update step they had to do for the pre-training. It's quite expensive. They used 4 to 16 TPU. On the contrary, fine-tuning is quite easy. They used only one single TPU, and within 30 minutes that was done. This is kind of the pre-training script which we can see is in the GitHub, Python run pretraining.py and give various parameters. However, this was written in TensorFlow 1, so it won't run in current version of the TensorFlow unless you downgrade the environment and do all those. So we had taken an approach that we'll build our own BERT in this video, right? When you have the longer sequences, we have problem in terms of pre-training. For example, if there are two batches, one is 64 batch, another is 256 batch. Although this batch size is less, because the sequence length is very high, 512, it is very expensive to train. It is very difficult to train that time. So they have given a trick. The trick is that suppose you have 100,000 steps. Then what you do, initially you train 90,000 step using 128 sequence length, and the remaining step you can train it using 10,000. That's the trick they're showing here. Long sequence are mostly needed for learning the positional embedding, and for this purpose obviously you have to create two data sets. Pre-training is costly, like we said. They have given an estimate of how costly is that. For example, in this case it has taken, if you have to train it on one single TPU, then that would run for 2 weeks continuously training them, has costed them around 500 USD. So the data preparation step which is required for BERT or any other such large model is very important. So we'll just go through how BERT data was prepared and then actually train our model using that. This is the link. This is the actual code. But nevertheless, we want to first give a small presentation, is summary understanding, so that it becomes very easy for you to either develop your own training script or understand that one better. So first we are doing a create training instance. How the data structure looks like is that there are documents which are separated by a blank space, and within each document you have multiple sentences. Each sentence has tokens, which is W1, W2 and all those words basically. So the first step we do, apply Unicode encoding, then do a white space tokenization, basically splitting the word by the white space in between. So each word becomes a token, simple tokenization. After that we infuse a BERT vocabulary file. The vocabulary will contain all the words which are relevant for the training task. And then we will be using the subword tokenization. This subword tokenization we already had learned during GPT. We used BPE there, byte pair encoding. Now we are going to learn another, which is the word piece. These are the most frequently used subword tokenization for transformer. So word piece is basically what it is showing is that it has got two loops. So the first is the outer loop, which starts and then it continues till the time the end of the word is reached. It starts from the 0. The inner loop, which kind of starts from the right hand side, so where it says that whether you have already reached the end of the position or not, and end is continuously getting updated by the inner loop itself. So what it does is that suppose you are taking a word called playing. Case number 1, when playing is part of the vocabulary, then what you do is that the outer loop starts from the 0 and end is 7, inner loop start, and then it finds that the entire word playing is already there in the vocabulary, so the loop ends, break. Case number 2, where playing is not there, so you have play and you have ing, two separate words which are there in the vocabulary. So you start the inner loop and then see that playing is not there, so you start reducing the index from the end. So you go from 7, then go to 6, 6 become play in, 5 which becomes this, and then 4 which becomes play. Starting from 0, ending it here. So you are increasing the index value from the right hand side. And the moment it finds the play as a word in the vocabulary, it breaks. Second, it goes start from this, offsetting the previously found play 4. So starting from here and then going to ing and found ing in the vocabulary, and it ends. So that's how it is basically creating subwords from a word, right? So end of the day, we can see from the document structure, it is basically list of lists. The first list is the list of sentences within the document, and the second one is the list of tokens inside that. After that, we do a shuffling, which means if this is document 1 to 10, then 10 becomes document 1 and stuff like that. Order, you are shuffling, right? But the order of the sentences are not shuffled. They are in order, right? And then you create an instance with some duplicates. What do you mean by create an instance? We'll just come there. But first, let us understand we are preparing this data for two type of tasks. One is the NSP task, and that is the next sentence prediction. In the next sentence, you are basically separating them by the separator token. You are also adding one spatial token, which is CLS. You are also 10% of the time, you are also adding some shorter sequence length so that not all of them look uniform, because that's what will be the real world example. So that's how the NSP data created. Then you chunk the sentences to the target sequence length. Okay, you don't kind of take all the sentences, but you just say that I'll take the maximum number of so much. That's how you are chunking them. Like sentence 1, sentence 2, and sentence 3. So although you have sentence 5, you have only taken the 3 sentences there. That's the chunk size. Then you say that out of this 1, 2, 3, I am saying that sentence 1 and 2 is my token A, which is the answer, question part, and the next part is the token B, right? Let me go there, and then you are attaching also a segment ID. Let me show this here. What do I mean? It's like this, segment ID. So token A example, where we are showing that you have this, token A example and sentence 1 and sentence 2, like I said. Often you will split them by 2 to mark them as what is sentence A and what is sentence B. So the token B example is sentence 3, and sentence 5 will be used as a random. Although I have taken sentence 1, 2, and 3, it's the chunk size. Sometime randomly, I'll go and take sentence 5, but not the document 2, no sentence from document 2. Within the document boundary, I will randomly go beyond the chunk and then take another sentence, which is randomly predicted. Giving an example here, what is the capital of France with a separator? Paris is this one. So the segment ID for the first part will be 0 and second part will be 1. This is important because this segment ID goes to the model along with the word embedding. That is one of the changes which you have to do in our code. Segment ID gives the signal to the model which part is question and which part is answer, or which part is the sentence 1 and which part is the sentence 2. And for model to get that sense, you have to embed them along with the word embedding. Remember this, in the code we'll show this once again. Fair enough. So that's what about the NSP portion of it. Then we are going to the mask LM prediction. How do we do that? We follow a rule. What token to be masked and what token not to be masked is here. This word of mask is used too many times in the transformer. We just want to refresh our memory that we have discussed mask or padding mask, which are essentially adding 0 at the end of the sentence to make all the sentences equal. That remains. That's called the padding mask. We had the causal mask or the look-ahead mask, which we have removed because we are doing only encoder only architecture. I want to give the bidirectional access to the token. So context, bidirectional access to the context. So therefore, this is not relevant for us anymore. And now we are talking about dropping some of the token from the model input. That is what is called the masking, and we call this as a prediction mask. Masking 15% of all the tokens that we have. Although prediction will happen for all the token, we will only calculate the loss for those masks. Okay. Now you can imagine that that is what is happening during the pre-training time. But when you are doing the fine-tuning, you are giving the whole data without mask. So there is a difference then between these two training. Now the pre-training data will be huge compared to the fine-tuning data, maybe some fraction, 1%, 2% or so. So that's how we are saying that even during pre-training time, a model has to have a sense that I will even have unmasked token. So as a result, that 15% whatever we have taken, from there we apply another rule. We say that 15% token whatever we have taken, from there 80% will mask, 10% we will randomly supply one token, and 10% time we will not change it at all, making it more akin to what during the pre-training what will happen. We are pushing in 20% changes or chances that they will look alike the pre-training, fine-tuning data. Giving a example of this, suppose this is a data, with quick brown fox jumps over the lazy dog. We are saying that these are our 15% token, brown jumps and dogs, out of which let's say the brown is actually the 80%, it falls under that 80% probability. So that time the brown will be replaced by mask. Jump, suppose considering that that is within the 10% time, then jump will be replaced by a random token like it, and dog will not be changed at all. So that's what we are saying here, right? Masking data is done. We not yet done. We actually give a masked position now. That's very important. Now we masked it, and we have to level them, that this which index position has been masked from the token and what is the actual token. If you have this 3 tokens which are masked, which index is 569, then that is what is actually masked LM positions. And the corresponding labels are, for 5 is jumped, 6 is over, and 9 is dog. Very easy to understand. So that's what is creating the masked LM position and mask LM label. Now we have a couple of things, which is the segment ID. We have the whether that next sentence is random, okay, or it is the logically next sentence. That is also there is next sentence. Masked LM position we calculated here. Masked LM labels is also available to us. So with that we create a class training instance, and then that becomes your create training instances. When we are creating this data were ready, we are creating actually initializing this instances from the class. Then we save them. Okay. Additionally, we also have something called a ALM masked LM weights. Basically, for each of this masking, we apart from calculating the loss directly, we can also associate one weight. We have not used it here, but that's kind of more flexibility of training, that when you do the prediction and there is a loss, all the losses are similar for all tokens, or you want to weight them. That's why this provision has been also kept here. Fair enough. Now I think this part is over. When you go to the fine tuning, this is the pre-training description. When you go to fine tuning, we'll understand from our code in more better way. Only two things we want to say here is that at the last we add a fine-tuned layer, like in GPT we had done, we can understand that all the other weight remain same, then you add another layer there which is task specific. Okay, in GPT it was the linear layer that we are adding, or a classification layer that we are adding. But the question is that in CNN, in the CNN transfer learning, if you have already studied CNN, then you will see the idea over there that you have the pre-trained model and you freeze those weight, add one extra layer and then only train that layer. In NLP you will see during the training you are not freezing those pre-trained layer, you are training the whole weight, all the weights all the layers you are training there. And why it is so, I just tried to get some reasoning for that unlike computer vision, NLP task gives some opportunity to learn even in the fine-tuning time. Those weights needs bit of modification, and that's what we are showing here. The data is less, but that's all. The other strategy that we can adopt to do this is basically layer-wise we can do a different learning rate. For the pre-trained layers, we can have a lesser learning rate, and for the layer which is task specific can have a higher learning rate. That's how also we can control all those. Some techniques basically, although we are not using it right now. But these are the idea in the NLP you can implement. Okay, let's go to our code now. So first of all, I am importing our previous models which we had built during the transformer tutorial. This is the from Euler scheduler, you are doing the custom schedule, you are taking the transformer encoder and the positional encoding. These are the three things which we had built. If you have not seen this, it's better that we go back and see that how we have built our own custom transformer, right? Now we are just importing those model and see how, if we have to build a BERT, what we have to do exactly, what changes are required there. Then we are going to the most popular transformer library, which is from Hugging Face, right? That simplifies the trading and etc. Right now we are taking the BERT tokenizer and the BERT tokenizer first. Otherwise we have to have our own vocabulary like we mentioned, and also do our own word piece sub tokenization. No need for that because this is already supplied by BERT, so you just want to take it from the Hugging Face transformer library, right? And these are all standard TensorFlow. At the very end, our model will be integrated with Hugging Face, and that's why these two will be required that time. Right now, let's focus on only our custom transformer and the data set which we are taking from the Hugging Face. So what is the data set we are taking? We are taking the Wikipedia dataset, and we want to see how the Wikipedia data looks like. We have used a little thinner model. Instead of 12 layers and 24 layers that the paper mentioned, we have kept it very low so that you can train it in our own computer, right? We just want to get the idea of what the pre-training means rather than actually doing the pre-training, okay? Which they have mentioned 4 days or 1 week it will take. 1 TPU to 16 TPU, we don't have those resources right now, so therefore let's take a smaller, just get the idea from here. Okay, so Wikipedia data is uploaded from this, and how does it look like? It looks like this. First of all, it has got 43,985 words in that one article. Article is like this. They have this paragraphs. Each paragraph will be treating as a sentence, and I am also showing some text from the very bottom portion, which is basically the external links. That's how you have one Wiki article, which is in our case is a document. So what we are going to do, we are writing this script here, writing this because those scripts which are there in the GitHub is dated, that may not run in your environment. So see how what we are doing. We are just giving a delimiter, along with there is a space to segregate one document from another. Document means article in this case. We are inserting this title as our delimiter, and then each of this paragraph we have kind of trimmed and created sentence from there. So sentence 1, sentence 2 to sentence 1, 2, 3, 4 are some of the sentences which I have taken. Then this next document is starting. So matches with our multiple documents. Within each document you have sentences, and these are the sentences which will be converted as token. After tokenization, you are doing the masking following the 80%, 10% and 10% rule. Remember that? That's what is happening here. So masking is done. Then for the NSP task, we are inserting the special token, the CLS class, which will actually extract the information whether this is a true or false next sentence or not, and the separator, that's what we are adding. We are also trimming them to the maximum sequence, this segment length. Then you are doing the pre-training data creation with the masking, where what is the important thing which we want to know here is that it is doing the token A and token B. How does it look like? It looks like this, you see. They are this word piece has an arc ism has been splitted into this 3 word as per the subword tokenization word, right? We explained how it happens, right? So these are the token which has gone inside the token A. These are the token which is token B, and this is saying that this is not random, it's the logical next sentence. Whereas some of them, like this one, has taken outside of this chunk size, and it is randomly picked up that within the document boundary. So that's the random text, right? Fair enough. So now you are saving this data, not required for this purpose, but just if you have done so much of hard work, you might as well save it, right? So after saving is done, you are loading this data into a load data set in a TensorFlow data set format, converting them as a tensor. And we know the instances, what it will have the input IDs, which are basically tokens, list of tokens. So this is sentence 1, this is sentence 2, and so on and so forth. It goes on. And we also have the segment ID for this, which means if it is sentence, the NSP sentence and etc., then the first part, which is token A, will have 0, and second part is this 1. This is what will be used as a embedding, added with the positional embedding, right? Okay. And then you need the masked LM positions. So he is saying that for this token, these are the places where we have masked, and actual tokens are this. This becomes our level. We tested it for one single instance here just to check that, let's say, if we are saying 0, 1, 2 is the masked token 103, and 13, you can also go there and see 13 is another token. So for them, what is the original token? We go back there and previous data and also capture this original one. So it is working here, right? Now coming to the model architecture, what we have to change is essentially the transformer encoder could have solved the purpose. Only thing we need to do is that add the self embedding as a learned layer, embedding layer. And this sentence embedding, when it is use this segment input which we are given in the data, that will be added with the positional encoding. So that's how the positional encoding layer is changing. Once we go to our transformer encoder layer, then we will incorporate that positional encoding along with this segment encoding, the customized one. So we are inheriting the previous module, the class, and then just substituting that. Okay, changes only that much. When you go to the model, then you are introducing this MLM dense layer and NSP dense layer. There are 2 layers which is required because it's a multitask objective, right? One is the next sentence prediction, another is mask language model prediction. So this is how the output from this model will be 2, MLM output and NSP output. So in this BERT model, which is the subclass of model, and encoder is basically this what we have customized, where you have the customized positional plus segment ID encoding done. plus the output we are changing. That's the only change which we need in the BERT model. Loss function, we again, because there are two output which are coming from here, we need to calculate the MLM loss and also the NSP loss, two losses. In the MSP loss, you can see that what it is essentially, it is telling that I want to first gather the masked position. So I have the full logits because it is predicting all words. I have the full logits available for each word I have. From there, only the masked position I want to calculate as the masked logit, and between the masked logit and the masked level, I just need to do the cross entropy loss calculation. Thereby I reduce, otherwise I had to map each word and see what is the loss calculation. Okay, and then when in the training loop we are using those loss function, plus we are giving a parameter to say that whether you want to only do the NSP tasks training for the NSP task, or you want to do MLM, or you want to do both. So that's a parameter which you are giving here. Now you are doing the pre-training using only MLM. Therefore, you can see task is equal to MLM. If we do so, then this is how it goes on. After 100 training, we see this MLM loss is very random, not coming down at all. Then we went through this joint task training, MLM and NSP, which is some improvement. Now the NSP is coming down very fast, but MLM is coming down very slowly, 8 to 7, 7 to 6, 6 to 5. And no wonder, that is why the paper said that they had to update for 1 million step, right? You can understand that why they required it. Anyway, so it reached 5.29 and we stopped the training there. We don't want to go for those 1 million update for 1 week, right? Okay, now we shape this model using Pickle, and then just compare the memory and the saved model just to ensure things are okay. And then we are seeing that this is kind of a 76 million parameter model. We have built such a small model even. Now moving to the fine-tuning. Pre-training is done. Fine-tuning. In the fine-tuning, you are not using the data set from Hugging Face. We are downloading it from the original squad URL. Somebody has given it, Raj Purkar. And then from there, let's see how the data looks like. The data, the first level is only version and data. Within the data, you have title and paragraph. We are interested in the paragraph. Paragraph is a list of dictionary which is there. And then within each of this item is again another dictionary where we have two keys. One is the question answer QS, another is the context. So how it looks like, if you look at the QS, then we see when did Beyonce start becoming popular? That's the question. Answer is also given that in the late 1990, and it is given that the answer starts from 269 character of the context which you have also supplied. So the training happens in this manner, that you ask a question and you also give the context. This is the para. Then you say that within this para, locate the answer. And the answer actually starts from the 269 character. Now when this answer is converted into token, you lose this 269 character because they are no more character. Each character is a token now. So their position will go different. It will be changed. That's why when you are doing this tokenization, the BERT tokenizer provide you this option called run return offset mapping. Okay, so return offset mapping will give you something of this sort, that you have converted the context as a token, fair enough. For each of this token, I have also given you something called this offset mapping. What it means is that suppose if this is the question, Beyonce, when did Beyonce start becoming popular? And we know the answer is in the 1990, and the answer starts from 269. We go to the offset mapping and see that where is 269? Here. And what is the index position of this tuple? So we know that position is basically 75. That's the index position in this tokens or the list of tokens. So the job for the model is going to be that given a question and the list of tokens, you go ahead and find out what is the start position of the token and what is the end position of the token. Then, once the prediction is done using this start position, you can identify that this is the token number, this is the token here somewhere in the 75 position, this could be the token, and then token to, number to ID to text, we can get the actual text, and we also know that is nothing but 264 or so is the position in the actual text. Fair enough. So like that, the the data set has been created with start position and end position. You are now changing the model for the fine tuning task. What is the change that is required? You are going to add this layer, which is a dense layer, which will have two output given. It has to give the start position and the end position. And for start position, you have to calculate the loss, what the model has predicted. You have given that label, and the end also you have to calculate separately. Correct? So it's a two output which you are getting from the model, start and end position, and you have the corresponding label, so you are calculating the loss twice here and returning it start and end logging. Therefore, now you are ready to upload the pre-trained model, which is basically within this model architecture. This is the new model for fine tuning. You are loading the old weights. That's how you are loading the pre-trained weight. And you remember this, skip mismatch may be required because in the last layer will not match here. That's how, or maybe the names are not matching. So once this model is loaded, you are ready to train it. And you can see that within very less time, I'm able to achieve to the 77% accuracy there. We are done with the pre-training. You got some idea. Now the last part is going to be, how do you now integrate this with your Hugging Face? Because that's very important. Pre-trained model, once you have developed, you want to now share with the world, and then people in the world, they need to reuse this pre-trained model and then train it. For all this purpose, the transformer library in Hugging Face is very, very super important there. So if we have not used a Hugging Face ecosystem to develop your model, are you gone? No, your effort is not wasted. This is how we will integrate it. It's a very important step for us. So basically, you take this library. TF pre-trained model is the which you inherit, and then start building your TF custom BERT model. What you do is that in the signature input parameter, okay, during initialization time, in the transformer, if you look at, we are giving all these values. What is the D model? What is the hidden size? And what is all those we are giving here? But now you need to give it with the format which Hugging Face suggests. So they have to be a config class. And then within the config class, you can just unpack here that the num layer is equal to config.num hidden layer. D model is config.hidden size. And DFF config.intermediate size. So the names are different here. But we know what maps here because we have very deep understanding of the transformer, right, from our transformer tutorial. Fair enough. And then rest of the things you see remain same. The call remains exactly same. You are giving this two output. You have this two signature method here, which is save pretend and then from pretend. Incorporate them there, and then you are ready. This model, this class is ready. In this class, you are again going to load the pretend weight, and config is initiated with all this parameter. So you instantiate this model with the config parameter, then load your pretend weight. So your effort of custom model building and training is not wasted. You still have a Hugging Face compatible model now. And then that model, you're just testing that, am I able to get the tokenizer for that? Am I able to do from the pre-train, I am able to load the Hugging Face stuffs are working here. That's what we tested. And once we are ready with all this, we have the option of uploading this model and share it with the world. So you just run this command from the command line, then enter your token, okay, which from the Hugging Face site you will be able to get the token, and then push the model here through this. It is pushed here. Once you push it, how does it look like? You see, you can see in the model list, your model will now be appearing. So this is my profile. I have one model uploaded. And if I otherwise come out from the profile and go to the model, there are numerous models which are there in the Hugging Face. In fact, when you are talking about all this Llama, Pythia, Bloom, etc., all are there in the Hugging Face. Somebody have built it and pushed it here. So you know what they have done in the background, right? So right now, our own model, Bhuja, it is there in the pretend model. It's a toy model, but nevertheless, this is a step taken to learn how Hugging Face can take your model. Okay, now once the model is there, you can kind of follow the, you can upload your model. Just instead of BERT based on case, you give your model name, and then the model will be available. Then you give the training argument, how many epochs and etc. And then trainer is the class which simplifies your training. So you can just do a trainer.train and give the Hugging Face compatible data. It will start training. So that's the part 3 of this, which is Hugging Face. That's the end of the session. We saw that there is a point, there is a time when actually Google overtook GPT. And then our next video will be even more interesting to see that what happened, how this wave of GPT kind of became a de facto standard, created the path for the large language model. That is going to be our next series of video. And as we have promised that from the recurrent neural network, we will go towards the large language model. We are really heading towards that in the next video. See you there in the next video then.